Okay, so yesterday we discussed the main steps of the algorithm. Let me quickly recap that and then we can analyze the performance of the algorithm today. That is the main agenda for today. And we should hopefully be able to do that quickly. So recall that the circuit for the Grover search essentially looks like this. So you have the all zero state, right? So imagine that you have to search over a database N, and imagine that so let me just be a bit more precise today about this. So this is what is called the ceiling function, right? Which means this is the closest integer, or rather the smallest integer that is greater than n, right? So the smallest greater than or equal to n. Actually, what I want rather is this, okay, the what is this called, the floor function, right? Okay, so the floor function would mean the um, largest integer that is smaller than this, right? So this is the largest, actually I should just say natural number, but anyway, smaller than 2 to the n, right? So the connection is that n, okay, should be smaller than or equal to 2 to the n. In particular, it is a kind of floor function in terms of the binary, in terms of binary, right? In the sense that I don't need more than little n qubits to represent capital N, okay? So 2 to the n is the closest power of 2 to capital N, right? And it should be such that it is the smallest power of 2 that is greater than n, okay? So the reason I'm saying all this is we'll revisit this floor and ceiling functions when we do the optimality of the search, rather the performance of the search algorithm. Okay, so first we prepare the data qubits. In the 0 tensor n state. The next step is to do a Hadamard tensor n, and that takes us to this uniform superposition state. Okay, and then comes the Grover iterate, G, right? And recall that G itself is composed of these various steps. So what we call G, this box, this has n data qubits, and it has some ancilla qubits. And this is basically equal to the following circuit, where you first apply the oracle for this search problem, right? And then on the data qubits, you have to do this inversion about the mean. That's what we called it yesterday, if you remember. So that involves, again, a Hadamard tensor n. It involves this phase shift operator, which is twice all zero minus identity. When I write zero, I mean the all zero, the n qubit zero, right? And then again, I have the Hadamard tensor n. And this is what the Grover iterate comprises of. And now I concluded yesterday by saying that the Grover iterate actually implements a kind of rotation, right? So that's the first thing I need to show today, that this is indeed a rotation. Okay, so this is the full Grover circuit. And then this has to be appended with this initialization stuff. And on the other side, you have measurements, right? So the final step. So the Grover iterate, what we will argue is that you need to apply this order square root n times, okay? And finally, measurement. Okay? And measurement in the standard or computational basis. Okay, so we were discussing the Grover iterate alone yesterday, and we were discussing this in a two-dimensional space spanned by two states that we defined yesterday, alpha and beta, where alpha is the set of all non-solution states, and this is the set of all solution states. I mean, uniform superposition of the set of all solution states. So let's say that there are n solutions to the search problem. Right? So if I want to ask, find all the, like this example I was giving someone at the end of class yesterday, find all the pizzerias within a 5-kilometer radius of my house, right? So obviously there may be more than one, right? And so let m be the number of solutions to the search problem. And then alpha becomes, and so we call these two sets as S and NS, right? So we said S is the set of all solutions, and there's m of them, and NS is the set of all non-solution states. So what do I mean by that? I mean that X belongs to S if and only if X is a solution. Okay? And this if and only if get X is not a solution. So then we will write down a uniform superposition of all the non-solution states, and that is ket alpha, and beta is the set of all solution states. And we discussed yesterday that this forms an orthonormal basis because alpha beta is 0 and alpha alpha beta beta is 1, because you have taken care of the normalization with the coefficients, right? And so this is a two-dimensional subspace of the n-qubit space, and I can represent it as a plane, right? It's a 2D subspace, 2D space. So this axis is what I will call ket alpha. This axis is what I will call ket beta. Where does our initial state lie in this? The initial state psi is obviously some superposition of alpha and beta, but it's not simply alpha plus beta, because alpha and beta have different weights, right? So psi is basically square root n minus m over n alpha plus square root m over n ket beta. Okay? Now let's put some angles to this. So let's call this as cos theta by 2 plus sin theta by 2. So where cos theta by 2 is square root n minus m by n, right? So you'll just remember these facts. So this is m by n. Okay. So this psi is now here. The initial state is basically some state like this. It's a vector in this plane, right? And this angle is basically theta by 2, right? Now what we showed yesterday is that the first step, which is the oracle, what does it do? The oracle acting on psi is going to mark all the solution states, right? So recall that the oracle marks all the solution states. So someone asked me yesterday whether this means that the oracle knows all the solutions. It is not that the oracle knows, it's rather that the oracle is able to verify the solutions. right? And the classic example again for this is the factoring, prime factorization problem, where finding the prime factors is a hard problem, right? No oracle is going to do that for you. I mean, and there's no point modeling an oracle as something which is just going to spit out the prime factors. Okay, that's an exponentially hard oracle, at least classically. The whole point of this oracle model is that the oracle is something very simple to implement. The oracle itself is not computationally complex because we never quantify the complexity of the oracle actually. The assumption always is that the oracle is something that is computationally easy to do. I think I mentioned this at the very beginning in the Deutsch or the Deutsch-Jozsa problem. But keep this in mind that the oracle itself is computationally easy. And that's why the complexity is quantified merely in terms of how many times you need to query the oracle, not so much in terms of how hard it is to do the oracle itself. So obviously your oracle cannot be something that just tells you the prime factors of a number, right? Like I believe someone used Google as an oracle when I said what are the prime factors of 5893. That's not the oracle. The oracle can do the following task very easily, which is I give a number and say check whether this is a factor of 5893 or not. That is always computationally easy. No matter how big a number you give me, doing a simple division is computationally easy. So checking whether something is a prime factor is easy, right? So just keep in mind that the oracle marks means that it merely verifies whether a given X is a solution or not. Right? And that is what this classical function f of x is supposed to do. The quantum oracle correspondingly, we saw this, it does -1 to the f of x for every computational basis state x, right? Where f of x is 1 if and only if x is a solution, right? So just note that it is not that the oracle knows the solutions, it can verify whether a given x is a solution or not. And the quantum oracle encodes that answer in this phase. And the job of the rest of the algorithm is to interfere this phase, is to make use of this phase interference and speed up the search. Because you have to search over, let's say if it's a prime factorization problem, you have to search over all numbers up to the square root of the number, right? So this is going to speed up that problem, not because the oracle is faster than the classical oracle, but because you are making the querying process faster. You're querying in superposition, you're putting the Hadamard tensor in, and then you're doing this phase shift operation, as we'll just see. So all of this together is going to speed up the process. I hope this clarifies the difference between knowing the solution versus verifying the solution. And all that the oracle can do is to verify, check. Okay, right. So after that spiel, let's proceed. So oracle acting on psi is going to, what is it going to do? So if psi is this state, cos theta by 2 alpha plus sin theta by 2 beta, what is the oracle going to do? Is everyone still around and awake?
Reflect the state about the alpha axis.
Correct. So what state will I get here? First, let's write that down and then we'll geometrically discuss that. So O acting on psi, it does nothing to ket alpha, right? Because those are the non-solution states. It now changes the relative phase like this, right? Because remember beta is a superposition of all the solution states, right? So this is what it's going to do. I once again note, okay, so I think this also someone has asked me in previous years, when I write down the initial state like this as a linear combination of alpha and beta, it is not that I know, once again, it's not that it's not that I prepare the state in this form. I am preparing only this state, right? Which is the uniform superposition state of all the computational basis states. And this is something I can always do. This form of ket psi is something that I'm using for my analysis. I hope that is clear. It's not that we are starting off by saying here are the solutions and they belong to this set, and no. You're preparing the state, in fact, you're doing nothing. You're preparing the all zero state and then you're doing Hadamard tensor n, right? So we know nothing about which are the solutions and which are not solutions. For the theoretical analysis, we note that this uniform superposition can be written like so. It can be written as this linear combination, and that then gives us this picture that there must be some angle theta by 2 that the psi makes with the non-solution axis. There is some other angle pi by 2 minus theta by 2 which it makes with the solution axis. And the goal of this algorithm is to somehow rotate this state closer to the solution axis with every iteration. Okay, every address to the query must somehow rotate it closer. Okay, so as Avik just pointed out, this is nothing but a reflection about the alpha axis on the 2D plane spanned by alpha and beta. Okay, so let's mark that here. Well, so there are actually two variations. So Avik is asking whether we know capital M or not. Okay, there are actually two variants of the Grover search. You can do one where M is known, and that's the simpler case. That's basically what we are doing now in some sense. Because that will tell you, because knowledge of M will tell you how many times you have to rotate. We'll see that right now. Okay, because the number of times you have to query the oracle depends on how many solutions there are. Okay. But there is also a quantum counting algorithm which can first count the number of solution states for you. Now, unfortunately, I don't have time to do that in this course, but I can refer you to the appropriate material for that. But so you can first do the counting algorithm, estimate how many solutions there are, and then run the Grover. Okay, so that's a kind of add-on or a variant to the Grover. Okay, so the first step is the oracle, and the oracle is basically going to do this. It's going to take this state to this state, right? Because it's flipping the beta coefficient, right? It's flipping the projection on beta, so that comes here. So this is the first step. This is just the oracle acting on psi. The next step is the rest of the Grover iterate. Remember, the Grover iterate has two parts. First part is the oracle. The second part is this, which is what I was showing you yesterday towards the end of class, was that this sequence of operations, Hadamard followed by twice projection on 0 minus identity followed by Hadamard, is nothing but a projection on psi minus identity, which in turn is nothing but a reflection about the state psi. So the next step, which is your Hadamard tensor n, twice 0, 0 minus identity, Hadamard tensor n, right? So this is nothing but, so let me write this out as, this is the all zero state minus identity. Then this gives me twice psi minus identity. And what is this operation? On this plane geometrically, this is a reflection about which axis or about which vector, about the vector representing psi, right? It's basically a reflection about psi on the alpha beta plane. Okay, so I hope you see that. I argued this yesterday by looking at the action of this operator on psi and looking at the action of this operator on a state that is perpendicular to psi. And then once again, therefore you can argue that in this 2D space, it's a reflection about psi. So this second part then is a reflection about psi, which means this state has to now be reflected about psi. So this then takes us somewhere here, right? And what is this angle? This angle is theta, so this angle has to be theta, correct? So this now is the final state with the entire Grover iterate acting on psi, right? Because remember, G is this operator, which is first oracle followed by, I'm just going to write it in this form now, twice projection on psi minus identity, right? Remember, this is the Grover iterate. And what we are seeing is that finally the net effect of this two-step process is for psi to get rotated to G psi, and G psi is nothing but a rotation of psi by angle theta. Okay, so I hope you see this, because the way I've argued it is, first of all, we note that this is a reflection about the ket psi, right? And this entire angle is theta, which means that this is now theta, right? So starting from a state of an angle of theta by 2 with respect to ket alpha, you've now moved to an angle 3 theta by 2 with respect to ket alpha, and you have moved that much closer to ket beta. Remember, ket beta is the solution axis. It is the axis that represents the set of solution states, right? Okay, so with this, what we have shown, therefore, is that while O psi just does this, right? That was the first step. The second step reflects you about psi. So finally, the Grover iterate acting on psi is now the state cos 3 theta by 2 alpha plus sine 3 theta by 2 beta, right? And now if we apply this G operation k times, so that is G to the power k, right? Then this acting on psi is cos 2k plus 1 by 2 theta ket alpha plus sine 2k plus 1 theta by 2 ket beta, right? So what we have established is a repeated application of G is rotating the state vector closer and closer to ket alpha, right? So yeah, what did I want? Yeah, so actually one can write this down as a rotation matrix in this two-dimensional space. So I think I will leave that as an assignment in the assignment for you, where you simply have to now express this operator in terms of ket alpha and ket beta, right? And show that, so actually this will again be an exercise. I think I gave another exercise yesterday. That you can argue that this, yeah, basically that, it's a kind of analytical argument to say that this conditional phase shift is basically what we called an inversion about the mean, right? This part. So that also I had written down yesterday's class. So today, let me say that this will be left as an exercise to show that in the alpha beta basis, which means that you're now visualizing G as just a 2 cross 2 matrix, right? Show that G is a rotation matrix which does rotation by angle theta, which basically rotates any vector in this plane, right, by angle theta. Any vector by, so I should say in the alpha beta plane by angle theta. Okay. So we are done basically analyzing the algorithm itself, but now comes the question, how many times do we need to apply K in order to reach close to a solution state, right? So now remember, so let's say that this is the final state, right? So the final state at the end of the algorithm, and let's say we do this Grover iterate K times, is basically a state of this form, right? It's still some superposition of alpha and beta, right? Now what happens when I measure? Because that's it, right? I'm going to apply, this is the final state that I have, and this state is now going to be measured in the standard computational basis, which is the X basis. Because remember, like I said, we do not know the alpha and the beta, right? Those are just convenient ways for us to analyze this state, right? We only know the computational basis, and we know that the solution is going to be one or more of this computational basis, right? So what happens when we measure this in the X basis? So if my state is like this, what is the probability of getting a solution state? Can someone tell me that?
Square term. No, sine square, sorry.
Ah, exactly. So the coefficient of the beta term, basically the mod squared of that is going to be the probability of finding a solution at any point. I can stop the algorithm at any point after any number of iterates, right? So I can stop it there, then the probability of finding the solution is simply going to be the mod squared of this, right? Because this ket beta itself is a uniform, remember it's a uniform superposition of all the solution states. So what this is telling me is that this is the probability, the sine squared 2k plus 1 theta by 2 is the probability of projecting onto ket beta. And once I project onto ket beta, then effectively measuring in the computational basis gives me one of the set of solution states with equal probability, right? So beta itself is a uniform uh, superposition of the solution states, right? So let's look at ideally how many iterations do I need if I want to exactly be on ket beta, right? So I hope you realize now that this is a probabilistic algorithm. So there is going to be a certain probability of getting the final solution state. And with every successive iteration, I'm going to get ideally closer and closer to beta, right? But suppose I want to be exactly on beta, what is the angle by which I need to rotate? So this is the starting state. That's square root n minus m over n alpha plus square root m over n beta. So what is the ideal angle by which I should rotate to exactly get to ket beta? So let's now look at the performance of the algorithm.
Pi by 2 minus theta by 2.
Okay, so I have psi as square root n minus m over n alpha plus square root m over n beta. This is where I'm starting, right? This expansion is basically telling me how the uniform superposition state, how far away it is from the set of solutions effectively, right? So now I'm going to write this as follows. So rotating by cos inverse square root m over n will take psi exactly to ket beta, right? Because I basically want to make the angle with beta 0, right? Which is basically pi by 2 minus theta by 2, right? As Nilesh was saying. So the amount by which I need to rotate will be this, okay? So now, but each step of Grover the search algorithm rotates by theta. So this then gives us a bound on how many times we need to run Grover, or how many times do we need to rotate. That's basically going to be cos inverse square root m over n by theta, right? And it's actually going to be the ceiling function of this, which means the smallest integer, but which is larger than this number. So I hope this idea is clear, right? If I rotate exactly by cos inverse square root m over n, then I exactly get to beta, right? But I can rotate only by theta each time. So I have to find what is the closest multiple, right, effectively. So this is the number of times that I ideally need to rotate. So now we need a bound on this, right, because in the sense, what, how do I now estimate this in terms of square root n? That's what the next few steps are about, right? So, well, so I said that rotating by cos inverse square root m over n takes psi to beta, but actually I don't need to exactly take it to beta, right? So let me rephrase this. So let's say that I want to get to within an angle pi over 4 of beta, which means I am in a state which is like this, right? So this will imply that with probability half, the algorithm returns a solution. So long as the angle that I rotate it to, right, is within something which is greater than pi over 4, right, then I know that with probability greater than half, the algorithm will return a solution state, right? So I hope this idea is clear that anyway it's going to be a probabilistic algorithm. So we try to get to within an angle pi over 4 to the solution axis. Okay. So anyway, let me look at this now, the cos inverse square root m over n by theta, and just try to bound it. And then if there are questions, we can look at that. Okay. So now let's say that m is much less than n. So we'll come to what happens when m is not so small. So actually you'll find that it's more advantageous for this algorithm for you to have fewer number of solutions. In fact, if you have just one solution, the algorithm works better, right? So then you know that theta, which is, okay, so we remember sine theta is square root m over n, which is very, very small, right? So then theta is approximately close to sine theta, which is, sorry, this is twice, sorry, sine theta by 2 is this, okay. So theta by 2 is approximately close to sine theta by 2, which is square root m over n, right? So then theta is then approximately twice square root m over n, okay? So how do we now bound this r? So let's just see what, so this cos inverse square root m over n is this is less than or equal to pi by 2, right? That's just because the overlap with respect to either of these, alpha or beta, is going to be within pi by 2, right? That's just a generic bound. So then we have this r, which was the ceiling function like this, becomes less than or equal to pi by 2 theta, right? And then if I use this already, right, which is that theta is approximately twice square root m over n, actually you don't even have to say m is much less than n. So actually here itself, right, then 1 over theta becomes essentially square root n by m, right? So using this itself, I can argue that this basically becomes pi over 4 square root n over m, and so this is then approximately order square root n over m, right? So the number of times that you need to rotate is bounded in terms of the database size and the number of solutions as order square root n over m. The other way to argue this without going through this is to simply say that, let's say that m is less than n by 2. Okay, so let me just say equivalently, say that m is less than n by 2. Let me say less than equal to n by 2. Then once again your sine theta by 2, which is square root m over n, right? Is then less than equal to theta by 2, right? So then once again you can use this to argue the same thing, right? Yeah, anyway, maybe the earlier argument itself was better. Let me not go through this, but the point is this, that this bound works whenever m is less than equal to n by 2, right? So then you can always replace this. So what I put as approximately here should ideally be of this form. So this, so let me rewrite it like this, that then theta by 2 is greater than equal to square root m over it, right? So this will then feed in here, right, to say that 1 over theta will be less than equal to square root n over m by 2, and so I get this bound, right? So long as m is less than equal to n by 2, this bound works. So let me quickly revisit the steps. I hope I didn't make too much of a mess of this. So what did we start with? So we started with this state, right? And then we said how many, by what angle should one ideally rotate if one has to exactly get to the solution state, right? But actually, we don't need to exactly get to beta. It is sufficient to get to within pi by 4 of beta, right? Within an angle pi by 4 of the beta axis, right? But in any case, so the cos inverse square root m over n is the angle by which we will need to rotate. And this is of course bounded by pi by 2. Each rotation takes us closer to beta by theta, right? So then this is the number of rotations that will take us to something which is very close to beta. That is r. And the simplest way to bound r is to say that this cos inverse square root m over n is less than equal to pi by 2. And then theta itself is bounded by twice square root m over n. Okay, so these are the only two steps that go into this bound, and so the number of queries to the oracle becomes bounded by order square root n over n, right? Questions? So the classical case is the number of queries you will need, or the number of steps, becomes order n. So actually I think it's order n over m. So this is exactly the square root of that. Okay. So this is what gets you the quadratic speed up. So you can in fact substitute this order square root n over m here and see what happens, right? So we have this final state out here, which is 2k plus 1 theta by 2 and 2k plus 1 sine 2k plus 1 theta by 2. So if you assume that theta by 2 is close to square root m over n, and then you put k is whatever, then you will k is this bound on the number of queries, you will see that you get something very close to beta, right? So you can substitute that here and get the exact probability if you wish. So yeah, the only other thing which I did not mention here is this part, which I've left for exercise. So basically what I want you to show here, and like I said, I might give this in an assignment, is that G basically is this 2 by 2 rotation matrix. So this is the key part of the Grover search, that you have constructed an extension of the oracle, right? What was your standard oracle in the Deutsch-Josa case? You have constructed an extension to the oracle, which basically is a rotation on this two-dimensional space spanned by solution and non-solution states. And this rotation each time takes you closer to the solution axis by an angle theta, and then you can use that to bound how many times you need to run the Grover iterate. Okay. So like I said, this works if m is much, much smaller than n. But what happens if there are many solutions? So what about, so this is the last thing I want to mention. So what if m is actually greater than n by 2, which means more than half the database is a solution? What happens? So go back and look at this angle. So what happens to this angle here? So remember that if m is less than n by 2, what's happening to this overlap angle with respect to beta? So m is less than n by 2, so m by n is less than or equal to half. So this coefficient is less than or equal to 1 over square root 2. So what can you say about the initial angle, the starting point of this state?
Less than 5.
The angle is less than.
Yeah, the overlap with beta is going to be an angle greater than pi by 4, right? So in the case of, okay, so no, I want to say it the other way around. So this angle, the starting angle with respect to alpha is going to be within pi by 4, right? But if the number of solutions is greater than n by 2, then you're starting closer to beta, right? Obviously. So where is this? Let me write that. Yeah. So this means that your theta is less, theta was sine inverse of, rather cos inverse of n minus m by 2, right? Where did I define theta? Yeah. So sine theta by 2 is then less than equal to half. So theta by 2 is less than equal to pi by 4. Your starting angle is less than equal to pi by 4, right? But if m is greater than n by 2, then your starting angle is something greater than pi by 4, right? Which means you're starting much closer to beta. In that case, actually the number of Grover iterates will actually take you, within a few iterates, you will go beyond beta, right? So this is a question that nobody asked me this time. What happens if you go beyond the beta axis, right? So what happens is now you add more dummy indices to your database, right? So add more dummy indices to your database, right? And then you can actually, so that, you can then, so in some sense, you can double the number of search entries to your data, the number of entries in your search, right? So that you now have m solutions, not in n entries, but in 2n entries. Okay, so then you're back to a situation. So if you call this some n tilde, then you're back to a situation where m is less than equal to n tilde by 2. Okay, and then all the other previous arguments go through. Okay, so this is the standard workaround that is used. Then you do not meet the constraint that m is less than equal to n by 2. Okay, is that clear? All right, so I'm going to stop here. Any questions?
So ma'am, in case m is equals to n,
M
that
is
means
equal to n.
that means everything is a solution. In that case, the psi will overlap with beta, right?
In that case, psi will be beta.
And and okay, so and in that case, we need not to add any kind of dummy.
Nothing, yeah. Psi is exactly beta in that case, right? So there is no, there's nothing to be done.
And
Just less.
if suppose the initial zero tensor and state which we pass through header mart,
Yeah.
and then and if we do not use, suppose I mean, yeah, okay. So suppose in place of zero, all zero, I am giving a particular n bit string there.
Okay.
And we remove this header mart and just pass it there. So it will either go to alpha or go to beta.
What do you mean?
Right?
I have some arbitrary n-bit string and then you're doing Hadamard tensor n. Okay.
No, I am not doing header mart tensor n. I mean, I'm just giving the single. I mean, it is just like us. We are checking that a single string, whether it is a solution or not. So in that case, it will just converge to either alpha or either to beta, right?
It will collapse to either alpha or beta. It will belong to either alpha or beta. Yeah. So you're picking some random ket x here, right? Depending on whether it's a solution or not, it will either belong to this superposition or this superposition, right? So yeah, it's like you're exactly either on the alpha axis or on the beta axis, right?
Ma'am,
Yeah.
ma'am, on the last case when m is greater than n by 2, in that case we are already starting closer to beta, right?
Yeah.
So, ma'am, after one rotation, we are moving farther from the beta axis, right?
Correct. Yeah. Yeah.
So can't we, decide that uh, zero number of rotation is good in this case? We don't need any rotation, so as to stay closer to the solution states.
Yeah, you're saying that you're already within pi by 4, the error
Right.
bound, so to speak. Yeah, exactly. You're already within your error bound of pi by 4. That's one possibility you simply measure, right? But if you want to improve your chances of getting a solution, this is one way of doing it. That just add dummy indices, query order n times, and then you will enhance your chances. You will not be close to pi by 4, but you'll be much more closer to beta. Right? So rather than probability half, you will have a much higher probability of getting a solution state. Indeed, yeah, what you're suggesting is also fine, which is that anyway, you've crossed the pi over 4 threshold. So with probability greater than half, you should get a solution if you simply do nothing. Right? Yeah, you could do
Yes,
that.
ma'am. Thanks.
But to improve your chances, it may be better to do this option. All right, so I think this pretty much covers what I wanted to say about Grover. There is one last bit, which is to argue that the Grover search is actually optimal, right? So I'll see if in the beginning of next lecture I have time to do that. I will make that argument. If not, I'll maybe write it up and just post it on Moodle or something. Okay. And Monday, then we'll start discussing the quantum Fourier transform. Okay. See you all on Monday.